Stephen Hawking was a remarkable scientist. He revolutionized our understanding of the universe. His work on black holes was groundbreaking. Hawking's theories continue to inspire research today. Hawking's brilliance extended beyond his scientific contributions. He was a gifted communicator. He made complex ideas accessible to the public. His book, A Brief History of Time, became a bestseller. Hawking's legacy continues to shape our understanding of the cosmos. Black holes are celestial objects with immense gravity. They possess such a strong gravitational pull that they can warp the very fabric of space-time around them. This warping effect is so intense that it can bend light, creating a phenomenon known as gravitational lensing. When light from distant stars passes near a black hole, it gets bent and magnified, allowing us to see objects that would otherwise be hidden from view. This makes black holes not just destroyers but also cosmic magnifying glasses. Nothing, not even light, can escape their pull. The event horizon, the boundary surrounding a black hole, marks the point of no return. Once anything crosses this boundary, it is inevitably drawn into the black hole, never to escape. This includes light, which is why black holes appear completely dark to us. The immense gravitational pull of black holes can even strip stars of their outer layers, feeding on the stellar material and growing in size. They are formed from the remnants of collapsed stars. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, shedding its outer layers. The core that remains can collapse under its own gravity, forming a black hole. This process is a violent and dramatic end to a star's life, but it also marks the beginning of a new cosmic entity with incredible properties. Black holes remain one of the most enigmatic phenomena in the universe. Despite decades of research, they continue to baffle scientists and astronomers. Their mysterious nature has made them a popular subject in science fiction, but the reality of black holes is even more fascinating. They challenge our understanding of physics and push the boundaries of what we know about the universe. For decades, black holes were thought to be completely black. The idea was that nothing could escape their gravitational pull, making them invisible against the backdrop of space. This led to the term black hole, as they were perceived as voids in the cosmos, swallowing everything in their vicinity. Nothing could escape them, not even information. This concept, known as the no-hair theorem, suggested that black holes could be fully described by just three properties: mass, charge, and spin. All other information about the matter that formed a black hole or fell into it seemed to be lost forever, leading to what is known as the information paradox. However, Stephen Hawking challenged this notion. In the 1970s, he proposed a groundbreaking theory that changed our understanding of black holes. Hawking suggested that black holes are not entirely black, and that they emit a form of radiation due to quantum effects near the event horizon. He proposed that black holes emit radiation. This radiation, now known as Hawking radiation, arises from the interaction of quantum particles at the edge of the event horizon. According to Hawking's theory, particle-antiparticle pairs are constantly being created and annihilated in the vacuum of space. Near the event horizon, one of these particles can fall into the black hole while the other escapes, resulting in the emission of radiation. This radiation, later named Hawking radiation, arises from quantum effects near the event horizon. It implies that black holes can slowly lose mass and energy over time, eventually evaporating completely. This revolutionary idea has profound implications for our understanding of black holes and the fundamental laws of physics, bridging the gap between quantum mechanics and general relativity. Hawking radiation is a mind-boggling concept. It emerges from the interplay of quantum mechanics and general relativity. At the event horizon, particle-antiparticle pairs constantly pop in and out of existence. Sometimes one particle falls into the black hole, the other particle escapes into space. This escaping particle carries away some energy from the black hole. This energy loss is what we call Hawking radiation. Testing Hawking radiation directly from a black hole is impossible. It's far too faint to detect with current technology. However, scientists have devised ingenious ways to study Hawking radiation indirectly. One such method involves creating analogs of black holes in laboratories. Recently, researchers conducted an experiment using a water tank. They created a region in the tank where waves could only travel in one direction. This simulated the event horizon of a black hole. Section 5. Waves and Event Horizons. An Unexpected Analogy. At first glance, water waves might seem unrelated to black holes. The two phenomena appear to belong to entirely different realms of physics. Water waves are a common occurrence in our everyday lives, while black holes are mysterious cosmic entities that exist in the far reaches of space. Yet when we delve deeper into the principles governing these phenomena, we uncover fascinating parallels that bridge the gap between the familiar and the enigmatic. However, they share some surprising similarities. Both water waves and black holes can be described using the language of physics, particularly through the concepts of waves and horizons. In the case of water waves, we observe how they propagate through a medium, creating patterns and behaviors that can be mathematically modeled. Similarly, black holes, with their event horizons, exhibit properties that can be understood through the lens of wave dynamics. Both water waves and light waves can behave like particles. This duality is not just a quirky feature of light but extends to other types of waves as well. In the realm of quantum mechanics, this wave-particle duality is a fundamental principle that helps us understand the behavior of particles at the smallest scales. It's a concept that challenges our classical intuitions and opens up a world of possibilities in understanding the universe. This wave-particle duality is a fundamental principle of quantum mechanics. It suggests that particles such as electrons and photons exhibit both wave-like and particle-like properties depending on how we observe them. This principle has profound implications for our understanding of the natural world, influencing everything from the behavior of subatomic particles to the formation of cosmic structures. In the water tank experiment, the researchers created a waterfall effect. By carefully designing the setup, they were able to simulate conditions that mimic the behavior of waves near a black hole's event horizon. This experimental approach allows scientists to study complex astrophysical phenomena in a controlled laboratory environment, providing insights that would be difficult to obtain through direct observation alone. Water flowed over an obstacle, creating a region where waves could only travel downstream. This setup effectively created a one-way barrier, analogous to the event horizon of a black hole, where nothing, not even light, can escape once it crosses the threshold. By observing how water waves behave in this scenario, researchers can draw parallels to the behavior of matter and energy near a black hole. This mimicked the one-way nature of a black hole's event horizon. The experiment provided a tangible way to visualize and understand the complex dynamics at play near these cosmic giants. By bridging the gap between everyday phenomena and the extraordinary events in space, such analogies help demystify the universe and bring the wonders of astrophysics closer to our grasp. Section 6. Detecting the elusive analog Hawking radiation. The researchers carefully observed the waves in the tank. They found something remarkable. In their quest to understand the mysteries of the universe, they had set up an experiment that mimicked the conditions near a black hole. Using a water tank, they created a simulated event horizon, a boundary beyond which nothing can escape. This setup allowed them to study the behavior of waves in a controlled environment, providing insights into phenomena that are otherwise incredibly difficult to observe directly in space. Near the simulated event horizon, pairs of waves spontaneously emerged. These waves were not just random occurrences, they were a direct result of the conditions created in the tank. The researchers noticed that these pairs of waves behaved in a very specific manner, reminiscent of the theoretical predictions made by Stephen Hawking about black holes. This was a significant observation, as it provided a tangible way to study and understand Hawking's theories. One wave in each pair traveled towards the black hole. This wave, much like the particles predicted by Hawking, seemed to be swallowed by the event horizon, disappearing into the simulated black hole. This behavior was crucial in validating the experiment, as it mirrored the theoretical expectations of how particles would behave near an actual black hole. The other wave traveled away. This escaping wave represented the particles that, according to Hawking, would carry energy away from the black hole. The researchers were thrilled to see this behavior, as it provided a clear analogy to the process of Hawking radiation, where particles escape the gravitational pull of a black hole, taking energy with them. This behavior is strikingly similar to Hawking's prediction. The data collected from the experiment showed a remarkable correlation with the theoretical models. The researchers meticulously analyzed the wave patterns and compared them with the predictions, finding a high degree of similarity. This not only validated their experimental setup but also provided strong support for Hawking's theories. The escaping waves in the water tank are analogous to the particles carrying away energy from a black hole. This analogy is powerful because it allows scientists to study complex astrophysical phenomena in a laboratory setting. By observing the behavior of waves in the tank, researchers can gain insights into the processes occurring near black holes, which are otherwise impossible to study directly due to their immense distance and the extreme conditions involved. This experiment provides compelling evidence for the existence of Hawking radiation. The successful replication of the predicted behavior in a laboratory setting is a significant milestone in the field of astrophysics. It not only supports the theoretical framework proposed by Hawking but also opens up new avenues for research. The scientists celebrated their discovery, knowing that they had made a substantial contribution to our understanding of the universe. This experiment stands as a testament to human ingenuity and the relentless pursuit of knowledge. Section 7. A validation of genius implications for Hawking's theory. The water tank experiment doesn't prove Hawking radiation definitively. However, it provides strong supporting evidence. It suggests that Hawking's theory, based on quantum effects near the event horizon, is on the right track. This finding has significant implications for our understanding of black holes. It suggests that they are not entirely black, they slowly evaporate over time, emitting Hawking radiation. This has profound consequences for the evolution of the universe. Section 8. Beyond the water tank. Expanding the horizon of research. The water tank experiment is just the beginning. Scientists are exploring other ways to simulate black holes in the lab. These include using Bose-Einstein condensates and optical fibers. Each method offers unique advantages for studying different aspects of Hawking radiation. By combining insights from these diverse approaches, we can gain a deeper understanding of this elusive phenomenon. Section 9. Unraveling the universe. One experiment at a time. The quest to understand Hawking radiation is far from over. It requires pushing the boundaries of experimental and theoretical physics, but the rewards are immense. By unraveling the secrets of Hawking radiation, we gain a deeper understanding of gravity, quantum mechanics, and the evolution of the universe itself. Each experiment brings us one step closer to unraveling the mysteries of the cosmos.